Hi, my name's Prof and welcome to Chemistry Matters, and today we are going to be talking more about enantiomers and what happens when you get more than one chiral center in a molecule. Okay. So let's pick up from where we finished off last time, okay? And that was in figuring out a way to denote enantiomers, okay? Now, sometimes you might hear me refer to these as optical isomers. That's another name for enantiomers. It's not particularly, well, it's frowned upon, let's say. So I'll try and stick with calling them enantiomers, but I may lapse. We'll see how we go. Okay, so this is where we finished up. And we said, okay, so there's ways that you can distinguish between enantiomers, okay? Between an S enantiomer and an R enantiomer, okay? And the way that you do that, again, you assign priority to the atoms that are attached to your carbon, your central, your chiral carbon, your stereocentre, and then you orient the molecule so that the least favoured is pointing away from you, and then you go from the highest priority to lowest priority and see which way you're going, clockwise or anti-clockwise. And that then determines R or S, okay? So R means that you are going clockwise, and S means that you are going anti-clockwise, okay? These, you might think, why don't they just call it C and A? Would have been a lot easier. R rectus, S sinister, right, left, okay? Sinister means left-handed, apparently, back in the olden days. Okay, so we talked about last time the fact that these molecules differ really practically only in their reaction with, or their interaction, let's say, with plane polarized light, okay? And we said that enantiomers will rotate the plane of polarized light an equal and opposite amount. So let's have a look now at a real life example of enantiomers rather than that just sort of made up one there. And let's go with these guys now. So these are molecules that we have already seen, okay? Two molecules that we've already seen. So this is, excuse me, butane, 2-ol, okay? So these molecules, butane 2-ol. Now, how do we know that they're chiral to begin with? That's the first thing that you need to do. You need to demonstrate that a particular molecule is chiral. Now that's easy when you've got one carbon atom in your molecule because you only have one to check. When you've got more than one, you've basically got to go through and check them all and see if they've got 4 different things around them. This one obviously doesn't because it's got 3 hydrogens. This one obviously doesn't because it's got 2 hydrogens. This one has 3 hydrogens. This one has, in this case, we're saying green is an OH group. White is a hydrogen. It's got a CH3 and it's got a C2H5. That is 4 different groups, okay? You might think that that's a carbon and that's a carbon, but it's the group as a whole. This is attached to O, H, C, and C. And of those C's, this one is not the same as that one because this carbon has got 3 hydrogens attached. This carbon has got 2 hydrogens and another carbon attached, okay? So that makes this carbon different from this one. We have 4 different groups around that carbon. Therefore, this is a chiral molecule. It contains a stereocentre. It will have, excuse me, a non-superimposable mirror image. Does it? Well, here's its mirror image. Looks like this. Can we superimpose them? You can try as hard as you like. You can't do it, okay? So, non-superimposable mirror images. Okay, so now we said that they have different interactions, equal and opposite interactions with plane polarized light. This will rotate the plane of polarized light plus 13.52 degrees. This will rotate the plane of polarized light minus 13.52 degrees, okay? And there are particular conditions that we measure these rotations under, okay? So particular concentrations, particular temperatures, particular sources of light, etc., etc. We're not going to go into that. We're just going to say that the rotation in this case is positive, and the rotation in this case is negative. Now, here's a really important fact that a lot of people forget. S and R are not related to plus and minus, okay? You can have an S enantiomer that rotates the plane of polarized light that way. You can have an S enantiomer that rotates the plane of polarized light that way, okay? So there's no relationship between S and plus or minus or R and plus or minus. They are entirely separate things, so don't get hung up on that, please. So that's pretty much all that we're going to do looking at molecules that contain only a single chiral carbon, or a single stereocentre. Okay, so what now about molecules that contain more than one stereocentre? So let's see what we can learn about these. Okay, the molecule that we're going to be looking at here is, in this case, a thing called 2,3,4 trihydroxy butanal. There's a mouthful. Okay, if we were going to draw the diagram of this, okay, it would look something like this. We've got an aldehyde here, we've got an OH here, we've got an OH here, and we've got an OH here, okay? Whoopsie. Let's draw that there just to keep everything fair and above board. Okay, right. So 2,3,4, 2,3,4, trihydroxy, there's 3 hydroxys there. Here's an aldehyde, and so it's butanal. Okay. So what have we got? When we look carefully at this particular molecule, we will see that here is a chiral carbon here, okay? And here is a chiral carbon here, okay? And so, whoopsie, let's take that off. Sorry, wrong molecule. So we've got a chiral carbon here, we've got a chiral carbon here. So 2 chiral centers, chiral carbons, stereocenters, call them what you will, in this particular molecule. So how does that affect the number of possible stereoisomers that we're going to get in this, okay? And there's a simple formula that the number of stereoisomers possible, so the number of stereoisomers is simply equal to 2 to the power of n, where n is the number of stereocenters in your molecule. Now this is the, in fact, let's say this is the maximum number of stereoisomers, because as we'll see, there are some situations where this doesn't necessarily apply, okay? So the maximum number of stereoisomers for a particular molecule is 2 to the power of n. In this case, our molecule has got 2 stereoisomers, has got 2 chiral centers, so 2 stereocenters, so therefore we would expect 4 stereoisomers. So let's see what these look like. Okay, so we've made models of these here. And what we might also do is draw these models out. Okay, so no, No, we'll just leave them as they are for the moment, okay? We'll just leave them as they are. Let's have a look at these as models of each other, okay? So you can see straight away, and I'm taking some liberties with my atoms here, but this is the aldehyde carbon atom. This is an atom that's got an OH coming off it. This is an atom that's got an OH coming off it, and this is your CH2OH, okay? Just to make it a little less confusing. If you put all the atoms in there, then you can't really see what's going on, okay? So again, this is the aldehyde carbon, this is a carbon with an OH off it, this is a carbon with an OH off it, and this is your CH2OH. Okay, so look at these guys. You can see straight away that these two are mirror images of each other, and that these two are also mirror images of each other, okay? Now, are they superimposable mirror images of each other? And the answer is no, they're not. You try and superimpose them, no matter how hard you try, it just doesn't work, okay? So these two are non-superimposable mirror images of each other. And these two, again, try and superimpose them. Nah, doesn't work, okay? Doesn't work. And so therefore these two are non-superimposable mirror images of each other. So these two are related as enantiomers. One of these will rotate the plane of polarized light one way, the other one will go equal and opposite way, okay? These two are also related as enantiomers, okay? Same thing. This will rotate the plane of polarized light one way. This will go equal and opposite amount, okay, the other way. So, where do we go with this? So, that's okay. So let's call this number 1, number 2, number 3, and number 4. So 1 and 2 are related as enantiomers. 3 and 4 are related as enantiomers. Great. You can see that straight away. They are non-superimposable mirror images. So we've got 2 sets of those. Okay, and we have our 4 possible stereoisomers. The formula says we've got a molecule that contains 2 stereocenters, so there should be 4 stereoisomers. There should be 4 ways of connecting everything up the same, but still getting different arrangements of the atoms in space. Yep. Now, the question then becomes, if 1 and 2 are related as enantiomers and 3 and 4 are related as enantiomers, how are 1 and 3 related? Okay, so let's have a look at them. Here's 1, here's 3. Excuse me. So let's have a look at them. How are they related? Are they mirror images of each other? So if we drew a line down here, does this go onto that as a mirror image? And you can see at the moment it doesn't, does it? Because the green and the whites are sort of around the wrong way. So if we rotate that around there like that so that the whites go the right way, then the greens and the reds are around the wrong way. And in fact, there's no way that you can do any rotations or anything like that to make this the mirror image of that. So these are related not as mirror images, okay? So these are separate molecules which are not mirror images of each other. In other words, they are stereoisomers that are not enantiomers, and so therefore 1 and 3 are diastereoisomers. Remember I said last time about that silly definition of a diastereoisomer being not an enantiomer or enantiomers. So these guys are isomers. Okay, 1 and 3 are diastereoisomers. You can do the same thing with 1 and 4 as well. And you can show that, again, there's no possible way that you can do anything to make those mirror images of each other. So 1 and 4 are also diastereoisomers. Now, what about 2 and 3? Okay, again, you put them together, you can flip them around any way you want, isn't going to work because these guys are also diastereoisomers of each other, okay? And 2 and 4 as well. 2 and 4 are also diastereoisomers. Again, they are not mirror images of each other, and so therefore they are related as diastereoisomers. And this does cause an awful lot of confusion in organic chemistry. Again, in my experience, the difference between enantiomers and diastereoisomers. And I think a lot of it comes down to the fact that diastereoisomers are defined really, really rather poorly, okay? But, you know, that's just my view of things, okay? So, of these 4 stereoisomers, 1 and 2 are enantiomers, 3 and 4 are enantiomers, 1 and 3, 1 and 4, 2 and 3, and 2 and 4 are all related as diastereoisomers. And there's your definition, essentially, of a diastereoisomer. That's what it means, okay? So, hopefully I haven't confused you too much with that. We are going to pick up where we left off in the next video, when we are going to be looking very particularly at molecules that look like this, with molecules or at molecules that have more than one chiral center, and that's going to lead us into a very, very important part of organic chemistry called carbohydrates, which you may have heard of, I'm sure. Okay, right, so that's me for this video. We'll see you on the next one. Take care, see ya.